maximize z equal to x1 plus 3x2 subject to the constraints minus 4x1 plus 3x2 less than or equal to 12, x1 plus x2 less than or equal to 7, x1 minus 4x2 greater than or equal to 2, and x1 x2 greater than or equal to 0. Here we can see that there are two variables x1 and x2 and three constraints. Two constraints are less than or equal to, and the third constraint is greater than or equal to type. Now the problem is converted to standard form or canonical form by adding slack, surplus and artificial variables appropriately. As the constraint 1 is of the type less than or equal to, we should add slack variable s1. Since the constraint 2 is of less than or equal to type, we have to add the second slack variable s2. The third constraint is of the type greater than or equal to, we should subtract surplus variable s3 and add artificial variable a1. After introducing slack, surplus and artificial variables, the standard form of LPP becomes maximize z equal to x1 plus 3x2 plus 0 into s1 plus 0 into s2 plus 0 into s3 minus m into a1 subject to minus 4x1 plus 3x2 plus s1 equal to 12, x1 plus x2 plus s2 equal to 7, and x1 minus 4x2 minus s3 plus a1 equal to 2, and x1, x2, s1, s2, s3, a1 greater than or equal to 0. This is the standard form of LPP. Now we can form the initial simplex table or the first iteration table. Here the basic variables are s1, s2, a1, and the coefficient of basic variables in the objective function becomes 0, 0, minus m. Then we write the values on the right side of the equation in the column of xb, that is 12, 7, 2. Then we have to write the coefficients of x1, x2, s1, s2, s3, a1 in the equation in this table. Next you write the coefficient of x1, x2, s1, s2, s3, a1 of the objective function as the values of Cj. Then we have to calculate z value equal to sigma Cb into xb, that's equal to 0 into 12 plus 0 into 7 plus minus m into 2. So the answer is minus 2m. Next to calculate Zj values, that's equal to sigma Cb into xj. So correspond to the first column, 0 into minus 4 plus 0 into 1 plus minus m into 1, that's equal to minus m. Similarly, we can evaluate other elements in that row. Then calculate Cj minus Zj, that is the net value, and we can see that the values are m plus 1, minus 4m plus 3, 0, 0, minus m, 0. If all these values are less than or equal to 0, then the solution is optimal. Here, otherwise, look at the maximum positive value Cj minus Zj. Here it is m plus 1, that corresponds to the variable x1. So the variable x1 will be the entering variable. Then to calculate the leaving variable, find minimum ratio, that is xb by x1 for x1 greater than 0. Here first value of x1 is minus 4. No need to calculate that value. Then 7 by 1 equal to 7, and 2 by 1 equal to 2. Of these values, minimum is 2. So corresponding to that 2, the variable a1 will be the living variable. Then that living row and the entering column intersects at the point 1. Then that will be the pivot element. Now we have to form the next iteration table. To form the next table, we have to make the all other elements in that pivot column 0. For that, we have to use elementary row operations. For that, new R3 equal to old R3, new R1 equal to old R1 plus 4 times new R3, and new R2 equal to old R2 minus new R3. Then the basic variables in the second iteration table are S1, S2 and X1, and the coefficient of these basic variables in the objective function of 0, 0, 1. Then the remaining values in the table are based on the elementary row operations. Then calculate Z value, Zj value and Cj minus Hj value as in the previous table. And from the net value you can see that the values are not less than or equal to 0. If the values are less than or equal to 0, then solution is optimal. Otherwise, look at the maximum positive value. It is 7. That corresponds to the variable x2. So x2 will be the entering variable. To find the living variable, calculate minimum ratio, that is xb by x2 for x2 greater than 0. And we can see that here only one value. So that is the minimum value that corresponds to the variable s2. So s2 will be the living variable. Then look at the living row and entering column. Then intersecting value is 5. So which is known as the pivot element. Now the pivot element is 5. Then make that pivot element 1 and all other elements in that column 0. For that, do this new elementary row operations. So new R2 equal to old R2 divided by 5 and new R1 equal to old R1 plus 13 into new R2 and new R3 equal to old R3 plus 4 times new R2. So the third table becomes, the basic variables are S1, X2, X1. Then the coefficient values are 0, 3, 1 and all other values we will get from the previous row operations. And we can see that the net values are less than or equal to 0. That means we reached the optimal solution, and the optimal solution is x1 equal to 6 and x2 equal to 1 and the maximum value is equal to 9.